All right, so the angle a vector makes with each of the coordinate axes, like we saw in that previous example, are called direction angles. So very important in practical computations, especially in fields such as engineering. So for example, in astronautical engineering, the angle at which a rocket is launched must be determined very precisely. A very small error in the angle can lead to the rocket going hundreds of miles off course. So direction angles are often calculated by using the dot product and the cosines of the angles, called the direction cosines. Therefore, we define both these angles and their cosines. So here is our definition. The angle formed by a non-zero vector and the coordinate axes are called the direction angles. For the vector. The cosines for these angles are called the direction cosines. So in the examples before, the direction cosines of our vector were cosine of the first angle, cosine of the second angle, cosine of the third angle. Right, so that was the 2 over root 22, 3 over root 22, and 3 over root 22 that we'd gotten. So the direction angles of that vector were the angles that we found, the 1.13 radians, the 0.877 radians, and the other 0.877 radians. So far, we've focused mainly on vectors related to force, movement, and position in three-dimensional physical space. However, vectors are often used in more abstract ways. For example, suppose a fruit vendor sells apples, bananas, and oranges. On a given day, he sells 30 apples, 12 bananas, and 8 oranges. He might use a quantity vector, Q, which is equal to the vector with components 30, 12, and 18. To represent the quantity of fruit he sold that day. Similarly, you might want to use a price vector, P, which has components 0.5, 0.25, and 1, to indicate that he sells his apples for 50 cents each, bananas for 25 cents each, and oranges for $1 apiece. So in this example, although we could still graph these vectors, we do not interpret them as literal representations of positions in the physical world. We're simply using vectors to keep track of particular pieces of information about apples, bananas, and oranges. So this idea might seem a little strange, but if we simply regard vectors as a way to order and store data, we find they can be a pretty powerful tool. So going back to the fruit vendor, let's think about the dot product of Q dot P. So we're kind of going in a different direction here. So this is sort of more of economic applications. So suppose we sell 30 apples at 50 cents a piece, 12 bananas at 25 cents a piece, and 18 oranges at $1 a piece. So what we can do is create a quantity vector which takes care of our quantities, and a price vector which takes care of our prices. When we use vectors in this more general way, there's no reason to limit the number of components to 3. What if a fruit vendor decided to also start selling grapefruit? In that case, he would want to use 4-dimensional quantities and price vectors to represent the number of apples, bananas, oranges, and grapefruit sold. and their unit prices. So as you might expect, to calculate the dot product of four-dimensional vectors, we simply add the products of the components as before, but the sum has 4 terms instead of 3. So all of the properties from previously smaller dimensions can just build, right? And that's sort of the idea here. So the total money made says we'll take the 30 times the 50 cents, the 12 times the 25 cents, and the 18 times the $1, or Q dot P. All right, so let's go ahead and take a look at an example.